Ever feel like you're just drowning in information?
Yeah.
Especially with AI, right?
Yeah.
One minute you think you're caught up, the next there's some huge leap forward. Well, it's exciting, but honestly can be a lot.
That's kind of why we do this deep dive, to cut through the noise and pull out the stuff you really need to know. So today we're digging into something called context engineering for AI agents. We're drawing heavily from a project called Manus, specifically insights from an expert, Yikao Pikji, our mission, to unpack the really practical principles behind how these agents actually work, things like speed, how they recover from mistakes, and how they scale up. And this isn't just theory, yeah. This is about what a team learned building something for millions of users. Real-world stuff. It's just amazing how fast AI moves. I mean, think back not that long ago. Improving a model meant fine-tuning. Weeks, right? Weeks per iteration, even for, well, what we'd call tiny models now.
Absolutely. And then almost like flipping a switch, you get models like GPT-3, FLAN-T5, and this whole idea of in-context learning with LLMs just takes over.
Yeah, it made those old ways feel kind of irrelevant overnight. Pretty much.
And what really grabbed me was how Manus saw this shift and went all in on context engineering. That's how they got improvements out in hours, not weeks.
Yeah.
They wanted Manus to be the boat on the rising tide, you know.
Right, not the pillar stuck to the seabed. It's a great analogy for adapting.
Exactly, agility.
And, making that bet wasn't exactly straightforward. It took a lot of experimenting. The team even jokes about their process, calling it stochastic graduate descent.
I like that.
Yeah, it's basically manual architecture searching, prompt fiddling, and empirical guesswork. Very candid. They actually rebuilt their agent framework 4 separate times.
4 times?
Wow. Each time, just refining how they handled context. It sounds maybe a bit messy, but that kind of hands-on, iterative approach, that's often how you find the real breakthroughs, especially in a field this new.
That makes sense. The scientific but maybe unconventional path. Okay, so as they were doing all this rebuilding, what core things did they figure out? Because one thing that jumped out from their findings sounds super technical, but apparently it's huge. The KV cache, they say its hit rate, is the single most important metric in production. Why? Why that specific thing? What makes it so critical for performance and, well, the bottom line?
It's a great question. And yeah, it really gets to the absolute core of agent efficiency. So think about how a typical agent runs. It gets user input, then it loops, right? The model picks an action, runs it in some environment, like Manus used a VM sandbox, gets an observation back, and then it adds that action observation pair back to the context for the next step.
Right, the context just keeps growing.
Exactly, it grows and grows. But the output, often just a structured function call, stays pretty small. Manus found their input-to-output token ratio was something like 100 to 1.
Whoa, 100 to 1. That's huge compared to a chatbot.
Highly skewed, yeah. And that's why the KV cache is king. See, contexts that start the same way, identical prefixes, can reuse the cached computations. This slashes the time it takes to get the first token out, and it cuts inference costs dramatically.
How dramatically?
Well, they gave an example with Claude Sonnet. Cached input tokens, 30 cents per million. Uncached, $3 per million.
10 times.
A 10x difference, yeah.
Yeah.
That adds up incredibly fast when you're operating at scale. So, okay, what does this mean for you practically if you're building an agent? First, and this is crucial, keep your prompt prefix stable, rock solid. A single token changing invalidates the cache from that point on.
Okay. Like what kind of mistake?
A really common one they mentioned, putting a timestamp, especially one down to the second, right at the start of the system prompt.
Oh, I can see someone doing that.
Instantly kills your cache hit rate for every single new request.
Ouch. Okay, stable prefix. What else?
Second, make your context append only. Don't go back and tweak previous steps. And make sure your serialization is deterministic, like JSON object keys. Some languages don't guarantee the order. That can silently break your cache.
Subtle. Right.
And third, sometimes you need to mark cache breakpoints explicitly. Some frameworks need you to tell them where the stable part ends. Usually, put that marker at least after the system prompt. And if you're self-hosting, make sure prefix caching is actually turned on, and maybe use things like session IDs so requests consistently hit workers that have the right cache.
Wow, okay. That 10x cost really drives home why you'd obsess over that prefix. So as agents get better, more efficient, they also get more tools, more capabilities, which leads to this other interesting challenge the Manus team talked about. The action space just explodes, especially if users can add their own tools. And counterintuitively, they found that a really heavily armed agent can actually perform worse, can get dumber. Yeah. Why is that? Why would adding more power make it less effective? How do you handle that complexity?
Yeah, it really fights your intuition, doesn't it? More tools should mean smarter. And the first instinct is often, okay, let's just dynamically add or remove tools from the prompt as needed. But Manus found you should really avoid that unless it's absolutely unavoidable. Two big reasons.
Okay.
First, remember the cache. Tool definitions usually live near the front of the context. Change them midstream. You just invalidated your cache again, back to square one on cost.
Ah, right back to the cache issue.
Exactly. And second, maybe even worse for the model's sanity if you remove a tool definition, but earlier parts of the context refer to actions using that tool.
Uh-oh.
The model gets super confused. It can lead to schema violations or trying to use hallucinated actions, basically tools that don't exist anymore in its current view. So Manus's fix was pretty clever. Instead of removing tools from the prompt, they mask the token logits during decoding.
Okay, logits masking. Explain that a bit.
Think of logits as the model's raw scores for every possible next token, like words or parts of words. Masking just means you tell the model, hey, ignore these specific tokens related to unavailable tools. Don't even consider outputting them right now.
Ah, you're guiding its output without changing the history.
Precisely. They use a context-aware state machine to decide which tools are allowed at any given moment. And most model providers actually support ways to do this, like response prefill.
Mm-hmm.
You can constrain the output. For example, in function calling, you might prefill the start of the reply for an auto mode, or prefill up to the function call token for required, or even prefill the name of a specific function if you need it in specified mode.
I see. So you're forcing its hand gently.
Right. And Manus also did something smart structurally. They designed action names with consistent prefixes, like browser for browser tools, shell for shell commands.
Makes sense.
This lets them easily restrict the agent to a group of tools just by constraining the prefix, often without using stateful logits processors, which can add complexity. It's elegant.
Very elegant. Constraining behavior without messing up the past context. Okay, speaking of context, modern LLMs, they have these huge context windows now, right? 128K tokens, even more. But the Manus team found something paradoxical. In real agent tasks, that huge window is often not enough, and sometimes it's even a liability. That seems totally backward. Why would more space be a bad thing?
Yeah, that one makes people scratch their heads a bit, but it comes down to, well, three main headaches they found. First, agent observations can be huge. Think about scraping a whole web page or pulling in a PDF. You can blow past even a massive context limit really easily.
Okay, sheer size.
Second, model performance often tends to degrade as the context gets really long. The window might technically fit it all, but the model might struggle to pay attention to stuff buried way back in the beginning, the lost in the middle problem.
Right, attention isn't perfect.
And third, just plain cost. Long inputs are expensive, even with prefix caching, because you still pay for every single token being processed.
So what do? You can't just chop stuff off.
Right. Exactly. Simple truncation or compression is super risky. You can't reliably predict which observation might become critical 10 steps later, lose something important, your agent might fail down the line. Any irreversible compression carries risk. So Manus's big idea here, and I think it's quite profound, is to treat the file system as the ultimate context.
The file system, like files and folders.
Exactly. It's essentially unlimited in size, persistent by nature, and directly operable by the agent itself. The model literally learns to write intermediate results to files, read data from files when needed. It's like using the disk as structured externalized memory. And their compression strategies. Always restorable. They might drop, say, the full HTML of a web page from the context if they keep the URL, or drop document content if they keep the file path.
So it can always get it back if needed.
Precisely. Shrinks the active context without permanent data loss. And this, leads to some really interesting speculation. Could mastering this kind of file-based memory make newer architectures like state space models, SSMs, which sometimes struggle with super long dependencies? Could it make them more suitable for agents? Maybe even finally realizing the old dream of things like neural Turing machines with external memory. It's fascinating stuff.
Mind blown a little bit there. Using the file system as external memory. That's powerful. Okay, let's shift to something that feels maybe a bit more human. Manus apparently has this habit of creating and updating a tudo.md file when it's working on complex tasks. You mentioned it's not just like a cute quirk, it's a real mechanism for the agent to keep track. What's the deep reason behind that?
You're right, it sounds simple, but it's a really clever way to manipulate the model's attention. Consider a typical Manus task might involve 50 tool calls on average. That's a lot of steps.
50? Yeah, that's complex.
And because the agent's brain is an LLM, it's vulnerable to drifting off topic or forgetting earlier goals, especially with long contexts or tricky instructions. It's that lost in the middle issue again.
Okay, so it can just forget what it was trying to do halfway through.
It can happen. So the solution? By constantly rewriting this tudo.md file, Manus is essentially reciting its objectives into the end of the context.
Ah, putting the important stuff right at the end where attention is maybe stronger.
Exactly. It pushes the global plan into the model's recent attention span. This cuts down on goal misalignment significantly. It's basically using natural language, the thing the model understands best, to constantly bias its own focus toward the task objective. No fancy architectural changes needed, just a simple file acting like a persistent reminder.
So the agent is literally giving itself a little nudge. Hey, remember the plan.
That's brilliant. Okay, this leads to another really interesting insight about, well, mistakes. Our human instinct usually is to hide errors, right?
Yeah.
Clean up the mess, pretend it didn't happen. But the Manus team found that doing this with AI agents, even though it feels safer, it actually comes at a cost. What's the downside of an agent hiding its mistakes?
Yeah, this one really challenges how we think about agent learning. The simple truth is, agents make mistakes all the time. Models hallucinate, tools fail, environments throw errors. Failure is not the exception, it's part of the loop.
It's unavoidable, basically.
Pretty much. And the cost of hiding those failures, of erasing the evidence, you remove the learning opportunity. Erasing failure removes evidence. And without that evidence, the model can't adapt. It has no signal that what it just did was wrong. So Manus's insight was powerful because it was simple. Leave the wrong turns in the context.
Let's leave the errors in there. Yes. When the model performs an action, gets a failure notification, sees the error message or stack trace, it implicitly updates its internal beliefs. It learns, okay, that sequence of actions under these conditions led to a bad outcome. It makes it less likely to try the exact same failing approach again. It reduces the chance of repeating the same mistake.
A built-in self-correction loop.
Exactly. And honestly, we started to think that error recovery is one of the clearest indicators of true agentic behavior. It's something you don't see emphasized much in academic papers or benchmarks, but in the real world, resilience, the ability to recover, is crucial. It's not just about perfect execution first time.
That's a really strong point. True intelligence isn't about never failing, but about how you recover. Profound. Okay, final big topic. Few-shot prompting. Usually seen as a helpful LLM technique, but again, minus how subtle ways can backfire, specifically in agent systems. How does a helpful technique turn into a problem?
It's another one of those interesting paradoxes, right? The problem stems from what LLMs are fundamentally good at: pattern matching, mimicry. They imitate the pattern of behavior in the context.
Okay.
So if your context gets filled up with very similar examples, maybe a few shot examples you put in the prompt, or maybe just the agent's own history from doing a repetitive task, the model starts to follow that pattern even when it's no longer optimal.
It gets stuck in a rut.
Precisely. They saw this with an agent reviewing, say, a batch of 20 resumes. After a few, it just falls into a rhythm, repeating similar actions, using similar phrasing, just because that's the dominant pattern it sees in its recent context, even if the next resume requires a totally different approach.
So it leads to drift or overgeneralization.
Yeah, drift, overgeneralization, or sometimes hallucination. It just keeps doing the same thing because that's what's familiar. So the fix: you need to consciously increase diversity. Manus found that introducing small amounts of structured variation in actions and observations helps break the spell.
Like what kind of variation?
Things like using slightly different serialization templates, maybe alternate phrasing for similar observations, even just minor noise in order or formatting. Just enough controlled randomness to prevent the context from becoming too monotonous.
Interesting.
So the key takeaway for you, the listener, is really don't few-shot yourself into a rut. The more uniform your context, the more brittle your agent becomes. A little bit of variety can actually make it stronger, more adaptable.
What a fascinating tour through the real nuts and bolts of context engineering. And I love that these aren't just abstract ideas.
Yeah.
These were lessons learned the hard way, right? Through repeated rewrites, dead ends, and real-world testing across millions of users.
Absolutely.
The Manus team is upfront. This isn't necessarily universal truth, but these are the patterns that worked for us. And that kind of practical, battle-tested insight, that's gold when you're trying to build these things.
Couldn't agree more. Look, context engineering is definitely still an emerging science. There's lots we don't know. But for actually building agent systems today, it's already absolutely essential. Models will keep getting better, cheaper, faster, sure. But like we've talked about, no amount of raw capability replaces the need for memory, environment, and feedback. How you structure that context, how you manage it, that's what defines your agent's real behavior. Its speed, its resilience, its ability to scale. It's critical.
So it's way beyond just picking the biggest, baddest model off the shelf. It's about designing the whole system around the model's interaction with its context,
That's it, exactly. The future of agents isn't just bigger models, it's smarter context.
which leads to a final thought for everyone listening.
The agentic future will be built one context at a time. Engineer them well.